Hey guys, so in the previous video we were talking about the three kinds of bonding: metallic bonding, covalent bonding and the ionic bonding. Then in the last video we talked about the ionic bonding, where the metal atom loses an electron, it becomes a plus charge. The non-metal atom will gain an electron, it will become a negative ion, also known as anion, and ultimately they form attractive forces between them. So for example, sodium has one electron in the last shell, it loses it. Chlorine atom has 7 electrons in the large shell, it gains 1 electron, so they both become ions, and they both have a noble gas-like configuration. Similarly, magnesium has 2 electrons in the last shell, magnesium lost 2 electrons, while the fluorine atom gains 1 electron. So technically it wasn't balanced. So we need 2 fluorine atoms, each one of which gains an electron, and you have 2 fluoride ions with -1 charge on each of the fluoride ions, and there is one magnesium ion with a charge of +2. Similarly, when we talk about the large scale, the big picture of the ionic bonding, we are going to talk about the structure of ionic bonding. So we are going to talk about the structure, what their structure looks like. So actually you will never have one positive ion individually and one negative ion individually. You have a negative ion and a positive ion like this. This is the positive ion, this is the negative ion, and you have, let's suppose in continuation, each positive ion is surrounded by negative ion and each negative is surrounded by the positive ones. So you will have it like this. You have your pair, which is, I'm copying it over here, and when I paste it, it looks something like this. So it's a continuation of the ionic lattice over here, and it's a really huge structure. I'll remove this portions over here, and this is a continuation. You see a lot of these structures continued. It's an ionic lattice where each positive ion and negative ion are surrounded by each other because of the electrostatic attraction. So the attractive forces between them are electrostatic forces of attraction over here between them. The attractive forces right over here are electrostatic attractions between the positive ions and the negative ions, and these attractive forces are really strong. So you have ionic lattice where there are so many positive and negative ions held together by strong electrostatic forces. It's really hard to overcome them. So that is why ionic compounds have high melting point and boiling point, because strong electrostatic forces are present. Strong electrostatic forces are present which cannot be overcome easily. You cannot just break them, you cannot just move the ions away from each other easily. So they need a lot of heat energy. They need a lot of heat energy to be overcome. You cannot overcome these electrostatic forces really easily. So the point is that when you talk about the forces of attraction between them, these are strong electrostatic forces of attraction over here. They need a lot of heat energy to be overcome. And this is the whole point, that why do they have high melting and boiling point? Ionic compounds do not have low melting point, they have a really high melting point. Next point is that ionic compounds do not conduct electricity in the solid state. You cannot have ionic lattice conducting electricity. Now why is that the case? They do not conduct electricity in the solid state. Do not conduct electricity in solid state. The reason is very simple, that the ions cannot flow. Electricity is the flow of some charges. So they do not conduct electricity in the solid state because the ions cannot flow in the solid state as they are tightly held, as they are tightly held in the ionic lattice. So within the solid state, they have a tightly packed ionic lattice. They cannot move. So that is why they do not conduct electricity in solid state, because the ions cannot flow as they are tightly held in the ionic lattice. But in the liquid state they can flow. So when you dissolve an ionic compound in a liquid state, they will flow. So if you dissolve this ionic compound, if I dissolve my ionic compound in a liquid state beaker, for example, this is going to be my beaker. If let's suppose I have a beaker, this is my beaker, let's suppose it's full of water, and let's suppose I dissolve my ionic substance. This is water over here. This is a beaker. This is water. And I'm dissolving my ionic compound. So what happens is the ionic lattice is broken down and the ions move separately. So these are my negative ions, remember, and these were my positive ions. So in the liquid state, they can flow freely. They can move to a certain direction depending on wherever they want to move. And as a result, the ionic lattice is no more there. So they conduct electricity in the liquid state. Conduct electricity in liquid state. Now liquid state can mean two things. It can mean molten, you can melt them, or it can mean aqueous solutions, as ions can flow now. The ions can flow freely now, and since they can flow freely, they can conduct electricity. So ionic compounds conduct electricity in liquid state because the ions can now flow freely. So we have talked about the ionic compounds, that they have strong electrostatic attraction between the ionic lattice, which is a 3D structure. They have a higher melting and boiling point because the strong electrostatic forces cannot be overcome easily. You cannot move the ions away. You need high heat to be given so that the forces can be overcome. Also, they do not conduct electricity in the solid state because the ions cannot flow. And when you talk about dissolving them, so once they are in a liquid state, then the ions can flow freely and they conduct electricity. So let's keep it till here, and in the next video we're going to be talking from scratch about the covalent bonding. Stay tuned, guys.